here we find ourselves in section 2.6. Section 2.6 is a great section because it really models something that you're going to have to do in calculus, and that is creatively think. Work within some conditions that are given to you and then create equations based on those conditions. And so the thought process, when I talk about creatively thinking, you might get the impression that it's hard. It really just isn't. It's not hard. It's just being able to look at the information and really understand what you've been given. And so a lot of calculus is getting everything into one single variable, and this section helps out a lot with that. So you'll see I've chosen about 5 problems for you to do in the homework, and I'll try to model them here. And so the first problem that I'd like to look at with you, and I'll try to draw a good picture, and that's what will happen in this section. Most will be given pictures. So for example 1, let me come in here and draw in black something. I'm going to put a set of coordinate axes in here, so they have a coordinate axes drawn. And what they have is they have the x to the 5th graph. So the x to the 5th graph is very similar to the x cubed graph. So this is y equals x to the 5th. It will just hug the x-axis a little bit longer and then shoot off to infinity. So we have that. We have a triangle that's being formed, and the triangle has a vertex at 0, 0, up here at a point 0, 4, and then directly across, oh, I'm sorry, that's not a 4, that's a y, 0, y. Can't read my own handwriting. Took notes on what the problem looked at. And then this is an arbitrary point on the curve, xy. Right? And so they would like us to get the area of the triangle that's formed. And so you'll recognize that they're going to be somewhat nice. What they gave you, and I'll come in here in red and just highlight, you absolutely know it's a right triangle. Those things are absolutely perpendicular because that line's completely horizontal that's touching the y-axis. And so because of that, you can use well, you'd use the area formula, but you know your height. And so what we do know is that the area of a triangle, go back to black, is 1/2 the base. Actually, let me write it like that. 1/2 the base times the height. So we're going to go back to a familiar formula. So that's all we need to do. And what we need to do is the directions are to find the area of the triangle as a function of x. And so when they say a function of x, know that what they want is only x's. So I need the area all in terms of x. So that you know the area is going to be 1/2. Well, what's the base? Let's consider the base to be this blue base right here along the y-axis. What's the length of that? Well, pretty obviously the length of that is y. So I'm going to put a y in there momentarily. And then the height, let's do the height in green. Here's the height right here. What's that height? Well, that's the distance x, right? They're telling us that right here, that it's over x up y, and that point right there. So that has to be the distance x. So as you look at that function, we got a problem. As I look on the left-hand side, it wants an area function all in terms of x. But as I look on the right-hand side, it's an area function that also, well, I don't know if it's an area function, but it has an algebraic expression that has both x's and y's. We got to fix that. So who's the problem? Well, the blue number is the problem. The 1/2's fine, and the x is fine. So what's the y? Well, the y we already know. Let me just go up here and show you. The y is x to the 5th. That's how high that is. If that's truly over x, that if this point right here is truly over x, then it's up a height of x to the 5th. And so what's the area equation? 1/2 x to the 6th. And we're done with that question. That helps so much in a calculus standpoint to have everything just truncated into one variable. And that's what they want us to practice with. So as we go to another example, this is a very classic example, this number 2. I've never seen a book that doesn't have it. And so what we have is like a rope, sometimes they'll call it, or a line, and we're going to cut it into 2 pieces. And out of one of the pieces, we're going to form a square. and out of the other one we're going to form a circle. And so they actually show you in the problem the best way to cut it. And so they tell you that this part up here, this upper part, let me put that upper part in blue. This part right here, the top part of the cut, they're going to say that that's a distance of 4x, a length. They just made it up. And so if you see that labeled out, you might wonder, well, why in the world did they call it 4x? Why don't they just call it x? Well, that's because they knew it was going to be bent into a square. A square has all sides being the same length, so because of that, you get a square with side length x. And it makes the whole math thing work out just perfectly. And so they actually have that. They said, hey, let's cut that into 4x. But I thought we should talk about why that was a wise choice. Because what's going to happen in a calculus standpoint is you're going to be making that choice, and you certainly could call it x. So, for example, somebody could sit there and be like, well, I would have called it x. Well, good for you. That's awesome. Now what you're dealing with is side lengths 1/4 x. That's fine if you're comfortable doing that. Know that you're going to find the area. So now it's 1/4 x squared or 1/16 x squared, and you forced yourself to deal with it, or probably most likely clear fractions. Well, who wants to do that? Make it nice. You can call it whatever you want. And so rather than call it x, call it 4 times the value of x. We actually don't care what x is. Well, we do in a way, but we'll get it all maximized in that whole process. So just think for a moment, if that's 4x, they're telling us the total length. I don't think I've shared that with you, so let me put that back in black. They're telling us the whole length is 16, so you took a 16, let's say 16 meter piece of string, and you cut it into 2 segments, one of them being 4x. Well, then the bottom one we know. We wouldn't want to call it y or anything like that. It's going back to your pre-algebra days where you would try your best not to use 2 variables. And so what is it? Well, it's the full length minus the top part, 16 minus 4x. And that 16 minus 4x is the circumference of this circle, because we're taking that green one and wrapping it around the circle. So the circumference of this circle, which we know is 2 pi r, is 16 minus 4x. Now that's important because what they want, here's their question: find the area of the 2 objects combined. Okay. Let me not put a comma. That's not appropriate. It just wasn't done as a sentence. In terms of x. Well, that's not going to be bad because we just have one variable. What is going to be bad is, and it's not bad at all, is us putting together that those 2 equations. So, and then they also say this: simplify as much as possible. And I'll show you what that is going to look like. Okay, got some cats that are going to be making some noise here. So if you hear some cats in the background, just ignore that. One just hopped up on the table, so we'll see what happens here. But here we go. Well, you know the area of a square. So let's talk about the area of this square. So I'm going to come back up, or maybe I'll stay here. So we have this square of side length x. Well, what's its area? Well, you know what the area is. The area is length times width, or of a square, the side squared. Well, what's the side length? So the area of the square is x squared. Easy. Well, what's the area of the circle? The area of any circle is, I'll put C for circle. The area of a circle is pi r squared. So we're a little bit stuck there. We don't know what r is, but we kind of do. We can use what's up top in green in order to help ourselves out. So let me translate that down here. So the total area that we're looking for of the objects combined would be the area of the square plus the area of the circle. Area of the square we're set on. Area of the circle is not in terms of x. But we do know something. We know that their circumference is equal to 16 minus 4x. Or, better stated, let me not put circumference in there. We know 2 pi r is equal to 16 minus 4x. So what do we know? we know that r is equal to 16 minus 4x all over 2 pi. Now you're going to be wise. You're going to reduce as much as possible. So let's look at all three terms that are on the right hand side. The three terms being the 16, the 4x, and the 2. They're all divisible by 2. So r is equal to 8 minus 2x all over pi. That's going to minimize our work. You could keep it as the big thing, but in the end you're going to have to simplify. And so we might as well clean up as much as possible. So what does that all mean? Well, how do we put that all together? Now the area of the circle, I did have a problem because it was in terms of r and I need it in terms of x, is pi times 8 minus 2x over pi, the quantity squared. So the area of the combined two figures is the area of the square plus the area of the circle. And this is the work that you're doing. A lot of upfront manipulation. What you'll find in calculus is that the actual calculus part is easy. It's the algebra manipulation they either allow us to start or the algebraic cleanup in the end that becomes the problem. And so what happens? Well, the x squared hangs out. But the computer would not accept this. We have to simplify it a little bit. So let's go simplify it. So I apologize. I didn't mean to put a plus there. So we have x plus, and we're just going to be patient here. 8 times 8 is 64. 2 times 8 is 16. Doubled is 32 x's in the middle. And we're really good at this by now. Just squaring out things by hand. If you need to do the full FOIL, do the full FOIL. Right? See the two 16x squareds in the middle, combine them to be 32. Won't take very long. Just remember on the bottom is a pi squared. Okay, to take that squared also to the bottom. Well, you got a pi up top and 2 pi's down below. So the only thing that's going to change as I go to my next statement is that the pi cancels. And the computer did take that as an answer. It didn't make me, I was afraid it was going to make me get everything over pi, but it didn't. So it probably has multiple variable answers that it could take. It just didn't take the one where I didn't fully multiply things out, so I wanted to be clear about that. So some things to remind you of is what you do is you just think through the problem, think about what you have, see where you're at, say, oh, I got an R, I got to change that out, what do I know? That's the type of thinking that we need to be in as we go into a calculus type of class. Third and final example from this section. In this part right here, we have the part of a parabola. We have a graph of 25 minus x squared. So we know what that is. So 25 minus x squared would be up here at 25. And it would peak right there. And it would open down. And it would be pretty... Right? It's only look steep because I'm calling that 25 because it's crossing here at the 5 level. You know what? I probably shouldn't draw it like that. I need to have a little bit more space for what I need to draw. So apologize for that. Should have thought that out a little bit more. Okay, so I'm going to come out here and just go really high up. Whoops, that looks even worse. Okay, come out just like this. And let me get rid of this right here. So pretend for a moment that this is 25 minus x squared. So this is the parabola 25 minus x squared. We're not surprised to see it opening down. This is obviously then 5. 5 is where it would be hitting that axis. And what they're doing is they're choosing an arbitrary point x here. And they're drawing a rectangle. And they want to know the area of that rectangle. Okay, so the area of the rectangle, this should be nice now. We know what area of a rectangle is. It's length times width. But they want to know the area in terms of x, right? So the area of the rectangle in terms of x, it's length would be, maybe we'd say y, and its width would be x. It doesn't matter. You know you can't have the y, so we're going to make sure we have everything in terms of x. So if this is over x, the y height is 25 minus x squared times x. Or what we have, what the computer took when I typed it in, it might have taken that. I didn't try. 25x minus x cubed. I just wanted to make sure it was going to take these things. They ask a really good question next. They ask, what's the domain of the function? Well, the domain is, think about this x. Where could this x go and start creating rectangles here in this first quadrant? Well, it can't go below 0. And it certainly can't go above 5. If it gets outside of that rectangle, then it has no upper bound, and so that's really weird. And so it's a natural domain of 0 to 5. The next question kind of surprised me. They wanted to know for what values of x was this a maximum. Now, from a calculus standpoint, that's a piece of cake problem to do. We would teach you how to find the derivative. We'd let you know that what the derivative, one of the things that it does is it tells you where you have maxes and mins. And when you looked at the derivative, it would be a squared function, and you would easily be able to solve that. The issue is that we don't know that. And so they're saying to use a graphing utility. So they want you to have a graphing calculator. There are graphing calculator simulators online that you can use, but you're going to basically have to use the trace function to find out where it's the maximum. And so I apologize for that. I'll look to avoid that style of question on the exam itself. But see if you could get a hold of an emulator. There's a TI, just type in TI-84 emulator and you'll find one, and just type in this function and it will graph it, and you'll be able to trace and find out where it has its highest value. Make sure you're on the range, the domain of 0 to 5 though. But it's not quite right in the middle. It's like at 2.83 or something like that for this problem. And then they want you to plug it in to know what that maximum A is, that maximum area. Again, you would never do this beyond this class, and because you would have something better. You'd have calculus that would give you not just the value that's the max, but the exact value. What your calculator is going to tell you is it's 2 point something. Well, that's an estimation. What would be better is for you to know the square root that's involved, the exact value, so that we care about the exact value, and calculus would help us in that regard. So again, foreshadowing some of the thinking that you're going to do in your next class, really challenging you to make sure you look at all the information that you're given, but a really great section. But the problems are kind of involved, so I only assigned 5 problems for you to just get a flavor of that. Have fun with it and let me know if there's questions.